Algebras are an important area of research in functional analysis, a branch of mathematics. A C algebra is a complex algebra A of continuous linear operators on a complex Hilbert space with two additional properties. A is a topologically closed set in the norm topology of operators. A is closed under the operation of taking adjoints of operators. It is generally believed that C algebras were first considered primarily for their use in quantum mechanics to model algebras of physical observables. This line of research began with Werner Heisenberg's matrix mechanics and in a more mathematically developed form with Pascual Jordan around 1933. Subsequently John von Neumann attempted to establish a general framework for these algebras which culminated in a series of papers on rings of operators. These papers considered a special class of C algebras which are now known as von Neumann algebras. Around 1943, the work of Israel Gelfand and Mark Naimark yielded an abstract characterization of C algebras making no reference to operators on a Hilbert space. C algebras are now an important tool in the theory of unitary representations of locally compact groups, and are also used in algebraic formulations of quantum mechanics. Another active area of research is the program to obtain classification, or to determine the extent of which classification is possible, for separable simple nuclear C algebras. Abstract characterization. We begin with the abstract characterization of C algebras given in the 1943 paper by Gelfand and Naimark. A C algebra, A, is a Banach algebra over the field of complex numbers, together with a map A. One writes X for the image of an element X of A. The map has the following properties: it is an involution, for every X in A. For all X, Y in A. For every complex number I in C and every X in A. For all X in A. Remark. The first three identities say that A is an algebra. The last identity is called the C identity and is equivalent to, which is sometimes called the B identity. For history behind the names C and B algebras, see the history section below. The C identity is a very strong requirement. For instance, together with the spectral radius formula, it implies that the C norm is uniquely determined by the algebraic structure. A bounded linear map, A/B, between C algebras A and B is called a homomorphism if, for X and Y in A. For X in A. In the case of C algebras, any homomorphism I between C algebras is non-expansive, that is bounded with norm permil1 currency. Furthermore, an injective homomorphism between C algebras is isometric. These are consequences of the C identity. A bijective homomorphism I is called a C isomorphism, in which case A and B are said to be isomorphic. Some history, B algebras and C algebras. The term B algebra was introduced by C. E. Rickart in 1946 to describe Banach algebras that satisfy the condition, for all X in the given B algebra. This condition automatically implies that the involution is isometric, that is, X equals X. Hence X equals XX, and therefore, a B algebra is also a C algebra. Conversely, the C condition implies the B condition. This is non-trivial, and can be proved without using the condition X equals X. For these reasons, the term B algebra is rarely used in current terminology, and has been replaced by the term C algebra. The term C algebra was introduced by I. E. Siegel in 1947 to describe norm-closed subalgebras of B, H, namely, the space of bounded operators on some Hilbert space H. C stood for closed. Structure of C algebras. C algebras have a large number of properties that are technically convenient. Some of these properties can be established by using the continuous functional calculus or by reduction to commutative C algebras. In the latter case, we can use the fact that the structure of these is completely determined by the Gelfand isomorphism. Self-adjoint elements. Self-adjoint elements are those of the form X equals X. The set of elements of a C algebra A of the form XX forms a closed convex cone. This cone is identical to the elements of the form XX. Elements of this cone are called non-negative. The set of self-adjoint elements of a C algebra A naturally has the structure of a partially ordered vector space. The ordering is usually denoted a per million. In this ordering, a self-adjoint element X of A satisfies XA per mil 0 yen if and only if the spectrum of X is non-negative, if and only if X equals SS for some S. Two self-adjoint elements X and Y of A satisfy XA per mil yen Y of ZA YA per mil 0 yen. This partially ordered subspace allows the definition of a positive linear functional on a C algebra, which in turn is used to define the states of a C algebra, which in turn can be used to construct the spectrum of a C algebra using the GNS construction. Quotients and approximate identities. Any C algebra A has an approximate identity. In fact, there is a directed family AII of self-adjoint elements of A such that, in case A is separable, A has a sequential approximate identity. More generally, A will have a sequential approximate identity if and only if A contains a strictly positive element, that is a positive element H such that H is dense in A. Using approximate identities, one can show that the algebraic quotient of a C algebra by a closed proper two-sided ideal, with the natural norm, is a C algebra. Similarly, a closed two-sided ideal of a C algebra is itself a C algebra. Examples: finite-dimensional C algebras, the algebra M, N, C, of NA, N matrices over C becomes a C algebra if we consider matrices as operators on the Euclidean space, Cn, and use the operator norm on matrices. The involution is given by the conjugate transpose. More generally, one can consider finite direct sums of matrix algebras. In fact, all C algebras that are finite dimensional as vector spaces are of this form, up to isomorphism. The self-adjoint requirement means finite-dimensional C algebras are semisimple, from which fact one can deduce the following theorem of Artina-Wedderburn type. Theorem: a finite-dimensional C algebra, A, is canonically isomorphic to a finite direct sum, where min A is the set of minimal non-zero self-adjoint central projections of A. Each C algebra, E, is isomorphic to the full matrix algebra M, dim, E, C. The finite family indexed on min A given by dim, E is called the dimension vector of A. This vector uniquely determines the isomorphism class of a finite-dimensional C algebra. In the language of K-theory, this vector is the positive cone of the Ko group of A. An immediate generalization of finite-dimensional C algebras are the approximately finite-dimensional C algebras. C algebras of operators. The prototypical example of a C algebra is the algebra B, H, of bounded linear operators defined on a complex Hilbert space H. Here X denotes the adjoint operator of the operator ZH. In fact, every C algebra, A, is isomorphic to a norm-closed adjoint closed subalgebra of B, H, for a suitable Hilbert space, H. This is the content of the Gelfand-Urey-Naimark theorem. C algebras of compact operators, let H be a separable infinite-dimensional Hilbert space. The algebra K, H, of compact operators on H is a norm-closed subalgebra of B, H. It is also closed under involution. Hence it is a C algebra. Concrete C algebras of compact operators admit a characterization similar to Wedderburn's theorem for finite-dimensional C algebras. Theorem: if A is a C subalgebra of K, H, then there exists Hilbert spaces I such that, where the direct sum consists of elements of the Cartesian product Ik, Hi, with T as 0. Though K, H, does not have an identity element, a sequential approximate identity for K, H, can be developed. To be specific, H is isomorphic to the space of square summable sequences L2. We may assume that H equals L2. For each natural number n, let Hn be the subspace of sequences of L2 which vanish for indices Ka per mil currency n, and let n be the orthogonal projection onto Hn. The sequence Nn is an approximate identity for K, H. K, H, is a two-sided closed ideal of B, H. For separable Hilbert spaces, it is the unique ideal. The quotient of B, H, by K, H, is the Corkin algebra. Commutative C algebras, Let X be a locally compact Hausdorff space. The space CO, X, of complex-valued continuous functions on X that vanish at infinity form a commutative C algebra CO, X, under pointwise multiplication and addition. The involution is pointwise conjugation. CO, X, has a multiplicative unit element if and only if X is compact. As does any C algebra, CO, X, has an approximate identity. In the case of CO, X, this is immediate. Consider the directed set of compact subsets of X, and for each compact K let Fk be a function of compact support which is identically 1 on K. Such functions exist by the Tietz extension theorem which applies to locally compact Hausdorff spaces. Fkk is an approximate identity. The Gelfand representation states that every commutative C algebra is isomorphic to the algebra CO, X, where X is the space of characters equipped with the weak topology. Furthermore, if CO, X, is isomorphic to CO, Y, as C algebras, it follows that X and Y are homeomorphic. This characterization is one of the motivations for the non-commutative topology and non-commutative geometry programs. C enveloping algebra. Given a Banach algebra A with an approximate identity, there is a unique C algebra E, A, and morphism I from A into E, A, which is universal, that is, every other continuous morphism I A B factors uniquely through I. The algebra E, A, is called the C enveloping algebra of the Banach algebra A. Of particular importance is the C algebra of a locally compact group G. This is defined as the enveloping C algebra of the group algebra of G. The C algebra of G provides context for general harmonic analysis of G in the case G is non-abelian. In particular, the dual of a locally compact group is defined to be the primitive ideal space of the group C algebra. C spectrum of a C algebra, von Neumann algebras, known as W algebras before the 1960s, are a special kind of C algebra. They are required to be closed in the weak operator topology, which is weaker than the norm topology. The Shermani-Takeda theorem implies that any C algebra has a universal enveloping W algebra, such that any homomorphism to a W algebra factors through it. Type for C algebras: a C algebra A is of type I if and only if for all non-degenerate representations I of A. The von Neumann algebra I A squared is a type I von Neumann algebra. In fact, it is sufficient to consider only factor representations, that is representations I for which I squared is a factor. A locally compact group is said to be of type I if and only if its group C algebra is type I. However, if a C algebra has non-type I representations, then by results of James-Glim it also has representations of type 2 and type 3. Thus for C algebras in locally compact groups, it is only meaningful to speak of type I and non-type I properties. C algebras in quantum field theory. In quantum mechanics, one typically describes a physical system with a C algebra A with unit element. The self-adjoint elements of A are thought of as the observables, the measurable quantities, of the system. A state of the system is defined as a positive functional on A permel 0 yen for all UA, such that I, 1, equals 1. The expected value of the observable x, if the system is in state I, is then I, x. This C algebra approach is used in the Haag-Kastler axiomatization of local quantum field theory, where every open set of Minkowski spacetime is associated with a C algebra. See also, Banach algebra, Hilbert C module, operator K theory, operator system, a unital subspace of a C algebra that is closed. Gelfand and Imerker Siegel construction, notes, Doran and Belfi 1986, ppA 5 6, 1. Doran and Belfi 1986, PA 6, 2. Siegel 1947, references, Arvson, W. An Invitation to C Algebra, Springer Verlag, ISBN A0-387-90176-0A. An excellent introduction to the subject, accessible for those with a knowledge of basic functional analysis. Cons: Alan, Non-Commutative Geometry, ISBN A0-12-185860 ZAM. This book is widely regarded as a source of new research material, providing much supporting intuition, but it is difficult. Dixmier, Jack, Lacey Algebras et les Repres Copyright Citations, Gautier-Villers, ISBN A0-7204-0762-1A. This is a somewhat dated reference, but is still considered as a high-quality technical exposition. It is available in English from North Holland Press. Doran, Robert S. Belfi, Victor A., Characterizations of C algebras, the Gelfand-Naimark Theorems, CRC Press, ISBN A978-0-8247-7569-8A. Emch, G. Algebraic Methods in Statistical Mechanics and Quantum Field Theory, Wiley Into Science, ISBN A0-471-23900-3A. Mathematically rigorous reference which provides extensive physics background. A. Eichstätt, C. Algebra, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Sakai, S., C. Algebras and W. Algebras, Springer, ISBN A3-540-63633-1A. Siegel, Irving, Irreducible Representations of Operator Algebras, Bulletin of the American Mathematical Society 53, 73 doi, 10.1090 per second 0002-9904-1947-08742-5A.